Hello everyone, welcome to our new video and the continuation of our tutorial problem on thermodynamics. Here we go. The problems: train transportation. The question: consider the Kaduna-Abuja train, which has a normal operating speed of 80 km/h. The train consists of a single locomotive and 10 passenger cars with a total mass of 4.4 times 10 to the power of 5 kg. It is being propelled by engine capable of converting energy from a fuel into mechanical power at a rate of 8.8 megawatt. On a particular section of the track, the train enters a speed of 70 km/h and an elevation of 0 meter, and exists at a speed of 35 km/h at an elevation of 300 meter. A. Estimate the minimum work transfer required to accomplish this change of state. B. The minimum time required to carry out the process. C. If at the exact speed of 35 km/h, an elastic spring is now used to bring the train to rest in 0.1 meter, what will be the spring constant of this elastic spring? That is a question. So here we go. This is a problem. Now let's use the thermodynamics procedure. So let's choose a system first. So our system, is train. We choose train to be our system, excluding the engine, excluding the engines. So train is our system. So now states. So we have initial state. We have given a velocity v1 as the initial state, that is 80 km/h, and you convert it to meter per second by multiplying by 1000 over 3600 seconds. This is meter, and this is the second. So that's the conversion factor, and when you do so, you will get 22.2 meter per second. Then the elevation at state 1, Z1, is 0 meter. So now state 2, we have given a velocity v2 to be equal to, after we convert as in we did in 1 by multiplying by 1000 over 3600 seconds, we will get 9.7 meter per second at an elevation z to 300 meter. So the interaction there will be no heat as we take the train as a system. There is no heat transfer considering the system. And then there will be a work that is used by engine to move the car. So work is not zero. Work is not zero. Now we apply the first law of thermodynamics. So the first law. So by applying the first law of thermodynamics, change in energy of the system is equal to the net heat minus the net work. So the net heat is 0. So the change in energy of the system is equal to the net work. So change in energy, that is the engine of the system, is equal to minus work net. So now let's find the energy of the system. So dE, that's the total change of energy of the system, that is the engine, is equal to change in kinetic energy plus change in potential energy plus change in internal energy. Now considering the system, there will be no change in temperature, so the internal energy is 0. Then we substitute. So the change in energy of the system is equal to we apply the formula for kinetic energy. We have a half m b2 square minus b1 square plus m g z2 minus z1. So that is the formula. So now we know this energy is the same as net work, that is dE of the system is equal to minus work net. So this implies that minus work net is equal to the change in kinetic energy plus the change in potential energy. So we substitute the given value, minus work net is equal to a half m. We have given the mass to be 4.4 times 10 to the power of 5 into b2 minus b1, that is we have 9.7 square minus b1, that is 22.2 square, then plus the kinetic energy. We have 4.4 times 10 to the power of 5 times g, which is constant, that is 9.81 times z2, which is 300 minus z1, which is 0. So this will be equal to 1.2071 times 10 to the power of 9 joule. This means that work net is equal to minus 1.2071 times 10 to the power of 9 joule, or we can say work net is equal to minus 1.2 gigajoule. So that is the minimum work required. Minimum work required to accomplish the process is 1.2 gigajoule. So that is A. Then B, we ask to find the time taken to accomplish the process. So let this time to be dt. Let this time to be dt, which is the one we are interested for. So the engine require 1.2 gigajoule to accomplish the process. So now we apply the equation, that is the change in time will be equal to the work required all over the engine's capacity. Engine capacity all over the engine capacity. That is power. It's like this is derived from work done is equal to power times time, or power is equal to work done over time. Anyone, so you can make T to be the sort of the formula. That is why we say work done is equal change in time is equal to work done over power. So that is the engine capacity is the power, that is the rate. So therefore we substitute the values, so the change in time will be equal to 1.2. We don't have minus here. We should not put the minus, because the negative sign is only showing the direction. Is it work is done on the system or work is done by the system? So this minus is so that the work is done by the system, that is the work required for the system to perform the action. So we have 1.2071 times 10 to the power of 9 all over the engine capacity, which is given h.h times 10 to the power of 6, which is equal to 137.17 second. So the time required is equal to 13.17 second. Then C. We ask to find the spring constant to which we use the spring to perform the action. So now if the elastic spring is used, work required to activate from 35 kilometer to 0. Use this to be an active work. So this will be equal to half m v square minus v1 square by applying the same principle you apply in model A. So this will be equal to a half into 4.4 times 10 to the power of 5 times 0 square, that is the final velocity, minus 9.7 square. So by doing we have minus 2.07 times 10 to the power of 7 joule. So this is the active work. So this work is opposite to what? Spring work is opposing to spring work. So we can say spring work is equal to minus the active work. So the spring work is equal to 2.07 times 10⁻⁷ joule. So now we go back to Hooke's law. So from Hooke's law, we know the spring work is equal to 1/2 K into x squared 2 minus x1 square. So this implies that 2.07 times 10⁻⁷ is equal to 1/2 K into x2 minus x1, that is 0.1 square minus 0 square. So by making K to be the sort of the formula, we got K equal to 4.14 times 10⁻⁶ kilonewton per meter, or we can just say K is 4.14 times just 4.14 giga newton per meter. So that is the spring constant required for this process. Thank you for listening.